Up next, we have Rod Soto and Joseph Zade from Splunk. Turn it over to you guys.
All right, good morning. And I'd like to thank the B-Size organization for having us. We actually did this presentation early this year at B-Size New York. We have updated it with new information, new data, and hopefully we'll have a bonus for you. It will give you a preview of an open source tool that we're going to release today at Black Hat Arsenal. If you were previously on the keynote, you probably heard a lot of truths about the mishaps of machine learning. We're not here to preach you on machine learning as a panacea, but we definitely believe it is an enhancer, and I would say a battlefield enhancer when you are fighting against cybercrime. We're still in the early stages though. So who are we? My name is Rod Soto, and I am a researcher with Splunk UBA, User Behavior Analytics, former Caspida. Caspida was acquired by Splunk over a year ago, and we were a startup that was using machine learning for user behavior analytics. Used to work at Akamai Technologies. I was the senior the principal researcher for ProLex and PLX cert. I like to break things, Palm botnets, and I play a lot of CTFs, and I develop a lot of CTFs as well. Then I have my partner in crime here, Joseph Zade. He is a senior data scientist at Splunk UBA, and we've been working together for over a year or so. And we do have for those who are here interested in this area and either have a data analytics or data science profile and security, it's usually good when both of them mix and they can talk to each other. A lot of times, and this is sort of like a tangent, in the industry, you'll find somebody that is a pure data scientist and they don't understand what malware is, for example. They see it as numbers. Or you have people that are hardcore security researchers but don't understand the concept of the statistics. So we've been able to have that synergy because we both have sort of a gradient where we work at one point and we're part of or interested in the hacking community. So in order for us to talk to you about machine learning, obviously we had to talk about the big data. Big data, as we all know, is something that is described as a bunch of variable, very large and fluid amount of data that cannot be processed by normal means, right? So with the development of big data, we had things like Hadoop. Hadoop is actually, in my opinion, a revolutionary technology. It's still advancing, but it gave us a way to use commodity hardware to do distributed processing and analysis of all this big chunk of data that otherwise would not be possible to analyze and make conclusions or assertions on it. So we're going to talk about the machine learning applied to security workflows and how it can help and its limitations. And we're going to describe a central nervous system approach to behavioral security. We're going to talk about the Lambda defense architecture. So as I said before, big data is obviously defined as a very large number of data that is very it's fluid. It changes constantly and is very large in size. So it's usually very difficult to process on its own, and it requires lots of processing power in order to be tackled. So right now, the way we see this, and sort of putting this together with current technologies and defense technologies, we have enterprises where there's a plethora of devices with lots of logs and alerts that are constantly producing data. And this data is distributed in too many places, and the analysis is usually slow. And a lot of these companies are using SIEM products, which they definitely allow us to put a lot of data together, but in certain cases, or in cases where decisions have to be made pretty quick, they fall short because of their limitations in processing power. So, like I said before, sim definitely makes life easier, but it sort of gets to a certain point where it's almost stagnant. And that's when technologies such as Hadoop provide an advantage to process this data and to apply machine learning technologies such as algorithms, and we're going to talk about that. We're going to talk about how you train algorithms, how you know when the algorithm is ready. Machines are like babies, right? So I hear sometimes when somebody says, yeah, I can beat a machine. Yeah, you can also beat my 8-year-old daughter in chess, right? Why? Because she's not trained. Once that machine is trained and has the knowledge and the experience that you have, it's going to give you a good run for your money, right? So sometimes seeing machines, I know sometimes we feel somehow nervous and anxious about the machines basically coming over to a workplace and probably taking over a lot of our work functions. So one of the things that we believe is that, for example, SOC 1 positions at one point will be taken by machine learning technology. And you'll see that as we move and we'll show you the architecture. However, we shouldn't be that anxious. This is a technology that is still in its infancy. This is a technology that can be understood, can be managed, and so far, it can be controlled. So here's one example of the utility of these technologies, right? It costs an organization an average of 1.27 million annually in time wasted responding to erroneous or inaccurate malware alerts. According to respondents, an average of 395 hours is wasted each week detecting containing malware because of false positives or false negatives. The extrapolated average value of lost time is estimated to be approximately 25,000 per week, 1.27 million each year for participating organizations. That was a survey that was done. And here it brings back what I said. You have an organization that's full of all these wonderful defense technologies. You have your pens, your FireEyes, your snorts, you name it. And all that data is going to the scene, right? But then you need this balances with people that are highly skilled and almost like intuitively knows what to look for, right? If you ever I worked at a SOC for 48 people. And it would take us between 6 to 8 months to get somebody up and running. And if you ever worked in a SOC, you know that the turnover is around 1.5 years, right? So we're talking about somebody you train for 6, 7 months, it lasts another 6 months, and then it says, I'm going somewhere else, right? So this is definitely a challenge. And these technologies can definitely help to improve detection and to provide us with means to tackle these issues. So I just said that about how SOCs are a challenge. They require training. And to be honest, until we train the machines and we get to a point where this technology evolves, it comes down to people versus people, right? People versus people means you as a skilled person, as somebody that can put yourself in the mindset of the attacker against the attacker. And we would talk about that in the adversarial drift and how that becomes a problem and it's a challenge that can be tackled with machine learning. So machine learning is basically a subfield of computer science that basically evolved from the study of pattern recognition and computational learning theory in artificial intelligence. Basically, with machine learning, we have the ability to process very large sets of data through distributed computing, plus the ability to apply algorithms that can learn based on these large data sets. And this provides analysts with more meaningful detection and actionable items, and you're about to see that. So when we talk about algorithms or learners, that's how they're known in machine learning. When somebody says learner, it means they're talking about an algorithm. So here's some generic definitions. So it's a process, a set of rules to be followed in calculation or other problem-solving operations, especially by a computer. These algorithms or learners can be designed to develop or scale against all the sources of data, which is what we're about to show you. One of the advantages of this is that by applying machine learning, you can complement static-based defense technology. So far, we have been depending on a static signature-based defense technologies. I'm telling you that because when I worked at Akamai, I would write snow rules all the time. And when we were looking at malware, it was the same thing. We were looking at static stuff. The attackers, either on DDoS or developing any type of malware, will obviously realize that we were creating signatures and then they will change it. And this presents a challenge. Sometimes during campaigns, you have a window after 10 or 15 minutes to come up with a signature that they know they're going to change. So definitely it is a challenge, and we can use these new technologies to tackle this problem. So by applying these learners, you can also build models, and these models can approach threats from a multi-contextual dynamic perspective. So we go beyond the static-based security technologies. So with that, I'm going to introduce my colleague, and he's going to tell you a little bit about sequencing the security DNA.
Can you guys hear me okay? Just a kind of brief intro about me. I'm a data scientist, so I take a lot of like the security language and I try to translate it to code basically. And part of the challenge in this problem space is usually when we're kind of talking about this stuff, and particularly these slides are just sort of translations of how a lot of like conversations that we've had with customers and basically pivoting back and forth between three languages, which is sort of the security-centric language, mapping these languages to an architecture or a platform, and also kind of expressing them using some ideas like statistics and machine learning and stuff. So kind of how this presentation fell together is we actually had to put some papers together for a conference called KDD, which is like a machine learning conference. So there might be a little bit dense definitions and stuff in here, but the goal is to sort of translate some of these things, these terms that are kind of floating around as a lot of buzzwords, particularly machine learning, and kind of map them back to your security intuition. And sort of one of the most interesting parts of working on like analytics or building like a big data application in cybersecurity, or more generally in any problem space where you're modeling an adversary, it's sort of a really interesting like corner case for artificial intelligence, because essentially what artificial intelligence is in some ways is taking an algorithm that's really good at generalizing information about known data or labeled data. And so what a label is a really kind of key piece of input for any of these algorithms we're going to be talking about. And in security particularly, you run into the problem of not having very many labels. That's already sort of like just kind of an accepted part of the space. And the other thing is, which is more complex, is the labels change over time. And this happens in sort of different scales. So I spent a lot of time modeling like just kind of covert channel type backdoor communication, C2, like malware beacons over the last few years. And it's really interesting watching how, like when we used to model HTRAN and some of these sort of classic rats, you could kind of rely on a steady sort of assumption of some kind of callback behavior over time. It might be randomized, but basically there's going to be a footprint on the wire at some point. Nowadays, like the in-memory malware that sort of persisted from the perimeter at web shells, like there's a really interesting, I guess it's a couple years old now, but it's a CrowdStrike talk called Beyond the Indicator, and I suggest you guys like check it out if you're interested in some of these sort of like the drift in some of these behaviors that back in the day you could just rely on a backdoor kind of leaving a network footprint at some point. Now they're just becoming much more stealthy in the sense that once the malware is basically it's residing in memory, and once the op is done, they can just drop it, and there's not even a file system footprint. So this is what we call kind of adversarial drift. Over time, the behavior of the model changes. And then the other kind of thing to be practical about, so this is a slide I took from security researchers named Monzi, and he uses this to talk to a lot of, to talk to customers about what it means to do defense at scale across like a complex threat surface. So part of the issue when you're doing like enterprise security is really, we're talking about many things we're defending against. We're talking about all kinds of different attack vectors, all kinds of different, like, depending on if you're in healthcare, you gotta worry about, you know, biomedical devices getting compromised. If you're in like the electric industry, now we're worried about IoT, and there's just, so depending on kind of where you're positioned in the enterprise or in a particular sector, there's many types of threats you have to worry about. And then the way it kind of helps to deal with this, both from a modeling standpoint and just from a security posture standpoint, is mapping kind of your security, your defensive posture and your point solutions or whatever defensive components you have to a model of the adversary. And I find this really useful in a very kind of mature way to sort of kind of break the space down a little. And that, hopefully that's kind of one of the good takeaways. I'm going to walk you through sort of what it means to like unfold a little like machine learning analytic as just a real simple proof of concept. And the idea is to show you that when we're running these algorithms, they're almost like hashes of information. You take a big piece of it, like labeled data, and the output is maybe a set of coefficients or a hash of some encoded information that we then use to do predictions on. And so in that sense, they're brittle by definition. So analytics, machine learning, all these buzzwords we hear, I would say, you know, like the nation state, and we hear at APT and some of these advanced threat actors, that's a game of human intelligence, much more than it is automation. We want to augment the human analyst as much as possible, but at the end of the day, it's much easier to build a machine learning analytic on like exploit kit samples. Like that's what we've been doing for Black Hat. We grab like a 400 labeled exploit chains, and we have the actual like payload delivery. And it's because it's generalized across many exploit kits. You know, there's some invariant behaviors in this sort of threat vector. And so I kind of think it kind of falls a little bit more in here where we're not dealing with adversaries who have like lots of resources who can kind of change and really stealthily hide their tactics. So so anyway, just to sort of like dive into like what we're doing here, it's basically just trying to accelerate some classic workflows. Like I've been kind of doing this off and on, more or less from like a consulting standpoint, just building custom solutions on top of like first generation SEM data. When the SEM data, like what happened with first generation SEM, like QRadar, Envision, some of these big systems that were sort of classic inputs to a bunch of different data sources. This is sort of like how the SOC in the last decade or so was basically landing all the data from a normalization standpoint and kind of triaging and escalating incidents in a day-to-day workflow. So kind of spending time in the SOC, you sort of realize there's a lot of these pain points, and Rod already touched on them. Part of it is just sort of like if you have an incident, like oftentimes to get a full picture of like doing the digital evidence collection, you have to touch a lot of different data sources. You have to correlate across different data feeds, you know, pivot off an IP address and, you know, look at the subnets around. And there's just, depending on kind of what problem you're looking at, there's sort of a search space you go through as an analyst. And this search space is pretty creative in some sense. That's why this is a hard problem to map to like an automated solution, because really depending on like the piece of evidence, the use case we're talking about, we sort of adjust our kind of search patterns and what it means to verify an event is a true positive or false positive, essentially. But there is benefit. Like I think that the point here, the message we're learning is for one, certain problems kind of will naturally be helped by some kind of algorithm that is essentially what I like to look at is like an optimization, really. So basically, we're just going to kind of walk through before we sort of show you like how we're applying these algorithms to sort of like a central nervous system approach at scale. This is sort of like what's happening with any one of these algorithms if we talk about it in some sense. Basically, this is kind of like a really hacky way to describe like a whole body of knowledge. But there's this idea in machine learning, like formally called VC dimension, and so this is sort of like if you're interested in the definition, like mathematically, this is sort of what we're talking about here. Basically, if you think about what it means to learn something, and we do this in our brain because you don't want to learn like something's dangerous every time you encounter it. We take hashes of the information and then we're able to do quick lookups so that I know, oh, a lion is going to kill me if I see it, instead of having to sort of reprocess that. And so that's kind of what happens with data too, with anything, in a learning workflow is you take a bunch of input data and there's some brain or some algorithm that processes the input, and it sort of creates like an encoding of what that input really means in some generalized sort of feature space. And so kind of just really quickly, basically what I just did here was I took sort of like R, this sort of open source statistical programming environment, and basically these are like default data sets in R. So all we did here was take an input data set, it's something to do with like cars. It just has a bunch of different stats about cars. And basically what we did was we fit a model. This is about as simple as a model as you can have in kind of these predictive models, and it's just a linear model, so it's a regression. You're basically fitting a line given a couple of predictors. So these are sort of the variables we are saying we're basically saying we want to model miles per gallon as sort of a linear combination of a couple of key variables, which is weight, displacement, and cylinder number. But at the end of the day, the point is what we're trying to show is we take some input, we model it with an algorithm, and the output of this whole process is basically like, these coefficients describe the line that we learned. So now, when I take a new data point and I predict using this model, I'm not using this big data set anymore. I'm just basically reading off this hash and saying, oh yes, are we on the line? Are we over it? Are we out? So you can get a lot of information from this. There's more information than here. There's metadata. There's sort of like have to kind of like assign significance and p-values and stuff. But in any case, like it's just sort of like a real kind of hacky way to explain the learning compression duality. So it's just sort of like, there's a lot of ways you can think about machine learning, and it's a buzzword that's thrown around a lot, but from a security standpoint and from any problem space where you're dealing with sort of changes in time over the underlying ground truth and also like adversarial drift, then I would say this is like something we have to use very carefully, and because it's a brittle process from these slides. Oh, and so here, if we have time, I'll show you the code that we were writing for this Black Hat project. And basically what we're using, it's kind of like well known that random forest, it's just a type of learning algorithm. You basically give it some input, and just like the linear model, it's going to give us a prediction. This is sort of what we're going to use because it's kind of best in breed. If all other things being equal, if we don't know anything else, it's sort of what I tend to try if I don't have a lot of time. And a lot of this stuff we're doing, just kind of like as a side note, basically the last 2 years since we've been part of the startup in Splunk, we've been leveraging a lot of open source Apache projects. So all these things we'll be talking about are essentially built with either Apache Storm or Apache Spark and some other things like MLlib. Okay, so this might be a little bit dense, but this is sort of basically this came from a conference called KDD, which is like a machine learning conference. So this is already kind of really academic. And I did my like grad school and stuff in math. So this is like some of the definitions here come from like, they're not security at all. Like particularly probably, the space of possible behaviors is a continuum at this point. Like I say this a lot to customers, and it's probably a worthless statement, but in some sense, like there's a lot of depth to this because this sort of represents the pattern we've been using to take an enterprise and decompose their threat surface into actionable units of kind of like TTPs essentially, or just a set of patterns that we want to model with an analytic or just augment a point solution signal. And so this is sort of how we kind of express this pattern in a really high level workflow that was meant for a paper, but that's essentially what I'm going to try and break down in some sense. So but basically, from a high level, we take a threat surface. And what I mean by threat surface, just really quick, is that, let me find it. So like a threat, like, this is kind of a bad picture. But like for a particular like environment, like I used to show this slide to a couple like large Fortune 500 companies when they would talk about like the 30 use cases they wanted to model and kind of handle from just from like where their SOC didn't have visibility. Like oftentimes like a great like question that comes up is like, how do we get more visibility in SSL traffic, or how do you know we have like some kind of covert channels over SSL, or how can we better find pass the ticket or golden ticket? Just depending on the use case, it turns out that you want to sort of enumerate the threat surface and then just start assigning either models or the way it's kind of described in this workflow is a family of models. So yeah. So in any case, if anyone's sort of curious about this paper or something, like it's sort of a work in progress, but come talk to me afterward. And I'll give you a copy of it and stuff. It's a little bit dense though. But basically, kind of like what ends up happening from a practical standpoint is what we're mapping. Essentially, there's two computational workflows, especially in these big data systems. They're called like real-time and batch workflows. And it turns out that if you sort of take any arbitrary behavior, basically you can kind of break them down into two sets of things, essentially, the sequential behaviors and non-sequential behaviors. And if you sort of expose this in the right way, there's basically like a system of workflows that map out how these behaviors are computed. And it sort of becomes like an architecture question at this point. So essentially what I've been doing from a modeling standpoint is taking like a real-time engine, like in this case it's Apache Storm, and then blending it with a batch engine. And then what happens is in this batch computational framework, like the reason we're sort of structuring it this way is all these sort of projects like are highly scalable on commodity hardware. So basically the number of clusters or the number of VMs I have is sort of like will kind of scale linearly across the number of users I'm analyzing in a whole environment. And so we're sort of like, what we're doing is like in first generation SEM, there was basically bottlenecks because these things were stood up on relational database backends. So you can't do like a complex analytic query. Like a good example is like PageRank, like an algorithm like PageRank, or some of these algorithms that are really graph heavy that process like really, they're basically large combinatorial optimization problems, or just large problems where they don't scale well across a relational database. And so we're kind of taking that pain that sort of has been felt in the enterprise for the last few years, and we're trying to kind of optimize around it. So when you kind of decouple the mutability of a transactional relational database in the back end of these architectures, then it lets you scale out much more complex analytic computations across individual users. So now, essentially what I do per user is I'm able to assign like a thread of memory or state per user in sort of in a highly parallelized way. And I just wanted to jump around a little because it's more like I kind of jumped ahead because probably I should have started with this picture, because this is sort of like what we're getting after is for a particular use case. Like, I mean, sometimes it's not users. It could be IP addresses. It could be anything that's sort of a primary key. But basically, I want to study their like a particular entity's behavior over time, either over sort of a batch workflow or a sequential workflow. So in this case, this is sort of a real-time computation where we're doing the analysis of exploit chains. And basically, what an exploit chain is, in some ways, is just a set of like interesting requests that will happen in a short amount of time. And if you start breaking down like the MIME types and looking at, I think there's an example in here. Yeah, so here's an exploit, basically an exploit sequence that happens in a really short amount of time. I think this comes from like some kind of exploit kit sample from Contextual. The point is here, like if we look at the MIME types, Yeah, so it's a text. Here's like the flash exploit. They're dropping a payload, and this might even be C2 at this point. So like basically, this happens in a really small amount of time. If you're a firewall and you're sort of like sitting in line, like looking at all these logs, well, the problem you have is that like there's going to be other people kind of in between, stuck in between here. So you haven't sort of sequenced the right way. Like basically, like it's hard for firewalls to keep state across multiple users at the same time, or anything in line, because basically hardware only has so much memory. So what happens is instead of like letting the hardware, the point solutions, have to maintain a bunch of state for every user in the environment, we just land these logs, to a SAM or for, basically like a data warehouse, and we're able to kind of essentially group by and sort. I mean, that's all that's sort of happening here. But basically, this sort of sequence of flows now lets us get a really simple picture. And so this is like essentially one use case and maybe in a bunch of different models that are focused on the sequential side of things. So that's kind of like, I mean, that's more or less sort of like the moral of the story at a high level here, what we're trying to convey.
Right. Just a comment about that. All this is done by centralizing. Remember what I said at first, that how we have all these similar sources of data, right? And then you had these tons of logs, like what we just saw in the getting the sequence or the exploit chain. You really can't do that. If you have a SOC analyst, he had to look at multiple sources, right? He has to go to a firewall, has to go maybe a TCP dump, maybe a FireEye, whatever it is. But it's very dissimilar. By us concentrating this in, sometimes you have to do some ETL, and I'm not sure if you guys know what ETL is. It's called extract, transform, and load. Basically, we're getting all the similar data sources and putting it into something that can be understood and then processed. By doing that, then we can apply the algorithm to it, pulling for all these multiple sources, right? So we just don't depend on just a firewall anymore, or even an expert eye. The expert eye you needed to train the algorithm, which he can tell you a little bit, and you'll see how the algorithm, sometimes you had to feed them with benign data, so then they can tell what malicious data is. So that's the context that we're looking in that slide, where we can actually, with the algorithm said, look, there is the sequence of MIME types. You have the text, HTML, Flash, or PDF, and then you have octet stream, and then you have some sort of a outbound or even SSL, or sometimes you have Tor. That happens a lot on exploit chains. So if you can combine that with other things, such as you have AD logs, for example, and you get a bunch of 40, I think it's 4624, which is usually related to pass the hash, or any other type of AD event that would spike at the same time that this was happening, or sequentially, then this gives you a strong indicator that something is going on. Whereas when I have all these dissimilar sources, or I just have a SIM which I have to constantly query, and it's based on a relational database, like he just said, there are limitations on getting to it. So I don't know if you want to add a little bit on the training of the algorithms?
Yeah, and that's essentially, so part of what I jumped around a little, but basically the goal here is describing a system that from if we're just talking about like Silicon Valley terms, what this is sort of reference to in the Valley is called like a Lambda architecture, which is a reference to a term Nathan Mars coined when he was working on the Storm project at Twitter. And there's sort of a whole interesting history here. This is really where the big data, in some sense, is very bleeding edge. And basically what we're taking advantage of the fact that there's first generation bottlenecks that are kind of well known in security workflows. We're kind of decoupling those bottlenecks by leveraging immutability in these different workflows in a very, very nice way. So the mutable side of all the state happens in this kind of real-time path, and because of that, a lot of things become really, really clean when you got to scale it. So one of the things that happens on these systems is they're learning systems. So then now we have to answer from an engineering standpoint, like, what does it mean when I don't have Rod or an analyst sitting down and kind of telling models to do things like kicking off a job, having a model to relearn. So we have to answer all these questions from an automated, from an API perspective, basically. And we have to implement something that this whole platform is monitoring. So I think even the system we're working on that's a commercial application, there's about 50 models right now. And that's really like the power of these systems that's the only way they're going to do anything for an enterprise is if you augment like existing signals with the power of many kind of analytics that are blended together essentially. And so all these models talk to each other. They're first-class citizens. We use Scala, so it's a very expressive language. And basically all these, like, so when I write a command and control model, I can kind of subscribe to the output of other models that are focusing on similar use cases or just maybe tracking users and combining the output of the peer groups for different users with kind of what a typical covert channel looks like. Just basically augments lots of signals together. And so there's an API that does all the learning for us. If anyone's, it's kind of like, this is sort of like another dense topic, but basically we sort of have a whole, for any model, how we update it in parallel is basically like a map and reduce kind of a workflow. So if anyone's sort of interested in these like really technical details, just come talk to me. This is part of this paper I can send you if you're interested.
You want to go a little bit on the limitations and challenges?
Yeah.
Because I want to see if we have time to show the tool too. Okay, so this is something that obviously the community is very interested in. Okay, so what is the extent of this? You hear things such as overfitting or underfitting. Overfitting is, for example, do you see that sequence of MIME types where it says, okay, there's Flash, and then there's text, then there is HTML, there is Flash, there is sometimes there's Adobe, then there's an octet stream. Well, overfitting would be, for example, if you have sometimes like a CDNs. CDNs become a problem because some of them behave like botnets. And if you actually look at the sequence of connections, then the algorithm starts saying, hey, there's an exploit here. So that's one of the challenges. It's called overfitting, right? So I see a certain sequence and start basically transferring that. So sometimes certain benign traffic, like CDM or video streaming, or sometimes when you have users that are using certain APIs, and these APIs have URI strings that suggest there's commands. And sometimes that becomes a challenge for the algorithms to say, okay, well, this looks like an exploit. So that's called overfitting. Underfitting is the opposite of it, which is the model is not trained enough, right? So like we said before you get those models ready, you had to be able to produce a benign type of benchmark so the model knows what is normal. And then you had to train on what is malign. And that's how eventually the algorithm can tell, okay, this is good or this is bad. But yet, you still had to tackle challenges. And those are principally for detection. They're very important, the overfitting, underfitting, because then what happens is, and this is from personal experience, the overfitting starts giving you a lot of false positives. And then once you start getting the false positives, then people start saying, okay, well, you're like X product, not, I mean, I guess we can put a name to each of them, right? Which is, it's full of, like somebody told me, my NUG was getting so many alerts from X product that we stopped looking at them, right? So that is a challenge right there that we're trying to tackle with this. So what is the response to that? The response is to refine the algorithm. Like, for example, we have a model that checks with the HTTP one is what, over 24 type of indicators, micro behaviors?
Oh yeah, I mean it's like 60 features.
There's like 60 features in every single HTTP connection. It looks at 60 features and checks, and then it does a statistical calculation. It says likely this is benign or likely this is bad. This is done in real time. That's why, like I said before, things like Hadoop is wonderful because it's what has allowed us to get to this point. The technology, obviously, as we have said it, this is not a panacea. This is like you saw in the actual screen of once we go to APD, this pretty much is very difficult, right? Even by applying the statistical logic, right? Because you just heard me say you had to feed a bunch of data. So if you have a once occurrence, how would you know? If it's a targeted operation, if it's a binary has never been seen anywhere, no IP rep, no virus total. See, there are limitations that we obviously have to tackle, but there is, what we're looking at this point is we're in early stages and we're looking more like the basic behaviors of detection, SOC 1, that we believe that eventually this in 5 years will probably replace SOC 1. So if you are at SOC 1 right now, you may want to start transitioning to SOC 2 because SOC 2 and SOC 3 are going to have to learn and take advantage from this technology, but definitely I'm telling you it's coming. And not only in just the log area, but in the network area and many other decision type defense or detection technologies. The operationalization, do you have any comments about that? As far as, well, you know, I call Hadoop sometimes magical, right? Like you look at it and you know, there's so many kinks and quarks that you really need a level of skill. And Hadoop is 100,000 pieces that you have to put together in the Hadoop ecosystem in order to make it work. So this is not something that we just can GitHub clone and that's it, or Docker and it's up and running. So that is definitely a challenge, and things like AWS and Cloudera, in my opinion, are positive. Provider of a way of streamlining and using this technology. And obviously, we had, like we showed, the adversarial drift, where, you know, just like they learn, like we learn from them, they learn from us, and they will continue adapting and improving their attacks. However, it is our opinion that as we train the algorithms, and as we are able to gather more data and apply it and improve our algorithms, the detection rate will improve. Would you like to show, can we show a little bit of the code? Or?
Oh, yeah, sure.
So basically, if you saw what you saw before, we show like a sequence of exploit chain. And what we will show you now is a tool that we're going to release this afternoon. That basically you will apply this to pickups, and then it will tell you what's the likelihood that there is an exploit chain and ransomware in it. We will publish it, so we want to give it away to the community so the community can work on it and improve it. And one of the nice things that we did was from the output of this tool, basically we created a script that SSH, I have a domain a laboratory where I have a domain controller, and basically you can grab for example, the name of the executable, create a PowerShell connlet, SSH into the domain controller, push a GPO, and then update the GPO, and the GPO will prevent from executing that malicious executable that you will get just from pickups. You just have to feed it the pickups, and then the two scripts will do it. So it's like an active defense script. So go ahead.
Yeah. So basically, what we're going to kind of show is part of the biggest, like the most painful part of these workflows from like any analytics application is creating this label right here. So like what we had to do basically, and this is kind of what we're open sourcing. Oftentimes the hardest part from like a security research standpoint for like big data is getting data that has the labels here. So we had, like some security researcher basically had to go through each PCAP or each, you know, like callback or essentially kind of layer 7 HTTP flow and kind of label, you know, good or bad, malicious or benign. So that's basically once you have these labels, that's when kind of machine learning becomes really applicable. But even when you don't have it, and that's why it's, for me, oftentimes it's like an optimization, because we sat down. This is sort of like the full kind of compute that we do per domain didn't fit on the slide, so this is just kind of like a couple examples. But we compute like a bunch of things. I'll show you a little bit in the code. But basically, these were sort of hand-tuned by some Mandiant guys, some really, and Rod, like just security researchers who are sort of mapping their intuition, what they hunt for, to kind of lightweight code. And what we ended up doing at first was just designing an algorithm that weighted some of these manually. So we didn't use any machine learning, we just used a heuristic, and we said, okay, a domain is bad. If AGD is sort of like a classic kind of computation here, if we see sort of randomly generated domains, that's kind of risky. If you see like a high number of null web referral, high number of null user agents, if you see kind of weird MIME type extension pairs, just a bunch of little things that you can kind of just adds the overall risk. So just real quick. So basically what we're kind of like on this repo I'll show you, we just have a bunch of different data sets. Like some of them are just Rod just doing benign traffic and us labeling it. And then having the algorithms, the algorithms can use that as input along with the exploit kits. Okay, so let's see here. What's the best way? Oh, you're not even on the, yeah, okay. Let's see here. Oh, sorry. So I'll just kind of show you very quickly, like what does it mean to build these like little, oops, sorry. So, like at the end of the day, actually, let me just pull up a better example. I'm going to make this full screen. I just got to find one little thing here. Timing behaviors. Okay. So at the end of the day, sort of what's the value of doing this just versus using like a regex or kind of a snort rule or something? Oh man, sorry. So, okay, this is kind of hard to see. But basically, like, what we're sort of able to do, so kind of like what I was showing you with this row of each domain, is we basically have these rules for different behaviors we're computing about a particular use case. And the thing is, I can, just for exploitation for URIs, I kind of studied the data, I looked at these exploit samples, and just derived some simple features, and basically are mapping this in a workflow that now, this is sort of what the learning algorithm is keying in on. And the power here is this is very expressive. I can write down anything I want. It doesn't have to be a regex, it doesn't have to be a snort rule. But I can add, you can add snort rules in. I can say, did I match on some level of criticality? We match on we blend everything. We blend Palo Alto rules, like semantic AV hits. These all kind of come in, so you get sort of a holistic view of the world. And so just, from a demo perspective, let me just show you sort of what the output is. Okay, here it is. Sorry. This is, okay. One last thing. So this is basically so I'm just at the jar here, and I'll just kind of show you let's see. Okay. So basically, if you clone this repo, what's the most valuable here is what's in data. So this is the majority of the work here. The code is just a proof of concept of some of these ideas. It shows an end-to-end thing, but the real value here is sort of already kind of going through this and labeling this stuff. And then, so what we do, can you guys see this okay? Is it big enough? Okay. Basically, what I'm going to do is just run through a demo. Oh man, I forgot to put one of the breaks in there. But basically what it's doing right now is the first step of a learning algorithm is learn from data. So I just point it to a directory. and it's just gonna like crawl the directory, and in this case, it's taking each labeled exploit sample and kind of deriving some of those features that I showed you in the kind of previous sort of in the development environment. And then so we take some good data, or should I say malicious data. There's only 350 or so samples, and then we learn from that, and then we learn from labeled benign traffic samples, and we build a model out of both those. And then when we want to score something, this was a little fast, but what happens is kind of here's the key prediction step. So I just passed a new model. It was basically it was like a ransomware sample that someone gave us. It was like it had the exploitation in it, and it's just kind of goes to show that if you sort of deployed this in line, the output is actually like an IOC of JSON. So when we see a good prediction, like okay, this is bad, then give us some indicators. We're just grabbing like the IPs, the domains, and the files in the PCAP right now, and then we're passing it to like another upstream workflow. That's kind of part of this like sexy ideas in automated response. In this case, we just created automated GPO object. So that's essentially sort of like, basically, if you have like 50 or 60 of these workflows, and you're blending them all together, that's sort of when these things become, practical for enterprise. But otherwise, it's sort of hard to scale some of these technologies down. But
I think we're up,
sorry.
right?
We got 1 minute.
Okay.
QA?
Do you have any questions?
Is the slide deck available somewhere so we can go back?
I think an older version is like on our LinkedIn, and maybe the old B-sides.
The old B-sides, yeah. We can upload it to the GitHub, and this will be uploaded. Is it available now, or?
Yeah, maybe we'll put it on the GitHub. So
We'll put it on the GitHub. We'll put the tool. We're gonna put the white paper so you can read a little more technical where we got all these indicators from, and then we're gonna give you the PowerPoints as well after we're done with Black Hat Arsenal today. So you just saw a preview of it. I wanted to really give this to Visas because I think Visas is super cool and an amazing conference. So if you don't have any questions, we'll thank you very much.
Yeah. Sorry, we didn't have a link in the other slide deck, but that's where most of the stuff is living.
Yeah, here's
Yeah.
Well, let's try that.
Oh, sorry.
Let's see, move it. That's it. Can you guys get that? So if you don't have any questions, then we'll thank you very much.